So Nikola Tesla once claimed that he could construct a complex machine, like entirely inside his imagination.
Right, just totally in his head.
Yeah, and he'd turn it on and let it run for weeks in his mind. And when he finally stopped this mental simulation, he said he could actually inspect the imaginary components for wear and tear.
Which is just wild.
It really is. He'd refined the design before he ever even picked up a single tool or built a physical prototype. It sounds like straight-up science fiction.
Oh, absolutely. It sounds impossible.
So we really have to ask, can extraordinary visualization alone actually create revolutionary technology? Or does an invention only become trustworthy after it survives the messy, unforgiving reality of, well, physical experimentation, measurement, engineering constraints, and public use?
I mean, that is the ultimate tension, right? Between pure inspiration and practical verification. We are so captivated by the idea of the lone genius pulling a perfect vision out of the ether.
Exactly, the light bulb moment.
Right, but the physical world is usually far, far less accommodating to pure imagination. The gap between a mental model and a working industrial system is just massive.
Well, welcome to this independent COSMORA HQ audio podcast deep dive. Today, we are on a mission to explore the principal ideas from the COSMORA HQ companion source for My Inventions, the Autobiography of Nikola Tesla.
And it's a fascinating source.
It really is. We are looking past the popular mythology to examine the actual mechanics of his mind, his inventions, and the actual systems he tried to build.
But before we step into his laboratory, we do need to establish a framework for you, the listener, regarding our source material today.
Right. Ground rules.
Exactly. Because an autobiography is, by nature, a highly crafted self-portrait. It's written from memory, often decades after the events actually occurred.
So subjective.
Very. So as we go through this deep dive, we will be deliberately distinguishing between his intimate autobiographical testimony, like his personal memories, and established science, like the verifiable laws of electromagnetic induction.
Yeah, we have to keep those separate.
We also have to separate documented historical records from his later massive engineering speculations that were proposed but, never actually proven at scale.
Okay, so starting where he starts, his childhood. The sources point to this really fascinating dual influence from his parents that kind of shaped how his brain processed the world.
Yeah, the contrast between them is striking.
Right. His mother had this incredible, practical, hands-on ingenuity. Like she was constantly inventing her own household tools and mechanical devices just out of necessity.
And then you have his father.
Exactly. His father was a clergyman, known for this intense discipline, a focus on really precise language, and just a massive intellectual range.
You can really see those two very different currents converging in his early development.
Oh, sure.
The manual, physical problem-solving that he inherited from his mother totally intersects with the rigorous, abstract mental discipline from his father. It suggests that his creativity wasn't just one isolated magical gift.
Right, it was a combination of things.
Yeah, it was a synthesized process. Visual imagination, verbal precision, and mechanical understanding were all sort of reinforcing each other from a very young age.
Though, reading his autobiographical testimony, it reveals that this visual imagination wasn't always a gift.
No, definitely not at first.
He describes experiencing unusually vivid mental images, sometimes accompanied by blinding flashes of light. It reads less like a superpower and more like, severe sensory overload.
Yeah, it sounds terrifying, honestly.
As a child, these visions were completely involuntary. Like if someone just mentioned a word to him, the image of that object would appear so vividly in his vision, he couldn't even tell if it was real or not.
He describes it as this overwhelming difficulty in his youth. But the crucial evolution in his method was how he learned to manage that sensory intensity.
How do you do that?
Well, over years of really intense mental effort, he trained himself to redirect those involuntary flashes into deliberate, highly structured mental control. Yeah, he essentially turned a neurological vulnerability into a private, disciplined mental workshop where he could manipulate variables at will.
When I read about him prototyping in his brain like that, my first thought was modern 3D CAD modeling. Or like a VR simulation just running on wetware inside his own skull.
That's a really good analogy, actually.
But I do have to push back on the reliability of this a bit. Isn't pure imagination inherently dangerous for an engineer?
Oh, totally.
Because without a physical reality check, your mind can just ignore the laws of physics if it wants to. Like in my imagination, I can build a car that flies, right?
Right.
But because I don't inherently understand the complex math of fluid dynamics, the aerodynamics of my imaginary car will completely fail in the real world.
That is the exact trap of unverified visualization. In modern engineering, pure imagination can actively hide errors.
Right, because you want it to work.
Exactly. The human brain tends to subconsciously ignore friction or heat dissipation or material stress because those things are inconvenient to the fantasy.
So how did his mental models actually work then?
Well, his internal visualization is best understood not as magic, but as highly disciplined pre-construction reasoning. The genius wasn't just that he could imagine a machine, it was his ruthless internal quality assurance.
He was actively trying to break it in his head.
Yes. He was using his intense focus to actively simulate physical resistance and wear. But even with that discipline, mental models are just a starting point. They must eventually face physical constraints, external tests, and independent evidence.
And his early attempts at building physical machines proved exactly that. The limits of internal modeling forced him into the physical world, which meant facing the harsh, necessary lessons of failure.
Right, because the real world doesn't care about your imagination.
Exactly. He built these early contraptions like pumps and turbines that completely failed or behaved in totally unexpected ways once they were subjected to real-world friction and pressure.
Failure is the unavoidable bridge between desire and mechanism. His early failed contraptions initiated him into the rigorous cycle of engineering.
The trial and error phase.
Yeah. Romantic enthusiasm might spark an idea, but progress only happens when a failure leads to strict observation, forming a new hypothesis about why the material failed, testing the new variable, and revising the design. The physical world always has the final say.
And he threw himself into that cycle with a terrifying intensity. Like, the source material details periods of educational excess that are, frankly, hard to read.
They really are.
He subjected himself to relentless, obsessive study regimens, completely ignoring sleep and nutrition, which resulted in serious physical collapse and severe self-neglect.
Yeah, he pushed himself way too far.
He was literally running his own body into the ground to keep up with his mind.
It is a stark reminder of the physical cost of his work. And when studying historical figures, it is vital that we don't romanticize their self-destructive tendencies as, like, a requirement for innovation.
Right, you don't have to destroy yourself to be a genius.
Exactly. Sustainable engineering relies on human limits and collaboration. Acknowledging his massive achievements does not require us to validate the destruction of his own health to achieve them.
But, I mean, out of this grueling, obsessive period comes the breakthrough that actually changed the world.
The alternating current motor.
Yes. This intense focus on identifying mechanical failures culminates in his work on the AC motor. And to appreciate this, we have to look at the massive industrial bottleneck of the era.
Right, the commutators and brushes.
Exactly. Direct current motors and early alternating current designs relied on these components.
Mechanical switching was the Achilles heel of early electrical engineering. Brushes were essentially these conductive contacts that physically rubbed against the rotating part of the motor, the commutator.
And they had to do that to reverse the electrical current?
Right, at precisely the right moment to keep the motor spinning. But because they relied on physical friction, they sparked continuously.
Which sounds incredibly dangerous and inefficient.
It was. They melted. They wore out quickly and required constant maintenance. They were inherently inefficient because, friction destroys energy.
So instead of trying to engineer a slightly more durable brush, or like a heat-resistant commutator, he steps back and completely reframes the mechanics of the problem.
He didn't just try to build a better brush.
Right. If mechanical switching is the flaw, he decides to eliminate mechanical switching entirely.
He fundamentally reimagined the electromagnetic relationship. He realized that if you use polyphase alternating currents, meaning two or more electrical currents that are out of phase with each other, peaking at different times, you could arrange them in a circle around the motor.
Okay, I am trying to picture this.
So as one current's magnetic pole weakens, the next one is strengthening. This creates a magnetic field that naturally sweeps around the inside of the motor in a continuous circle.
So it's pulling the rotor along without anything physically touching it to switch the current.
Exactly that. The magnetic field itself rotates. The changing currents do the work that the mechanical brushes used to do. He removed the physical friction from the core operating principle, creating the induction motor.
It is a beautiful piece of physics. But what stands out in the sources is that inventing this elegant motor wasn't enough to change society.
No.
The induction motor was just one node in a massive interconnected system. For that motor to turn in a factory, you needed polyphase generators at a power plant, voltage transformers to step the power up for long-distance travel, transmission lines.
And step-down transformers at the destination.
Right. He didn't just invent a device. He had to architect an entire grid infrastructure.
And that transition from device physics to system architecture is where many brilliant inventors fail. Infrastructure only succeeds through compatibility.
It makes me think of, like, a smartphone.
How so?
Well, inventing an incredible induction motor without an AC grid is like inventing the world's most advanced smartphone in an era without cell towers or standardized chargers. The device is functionally useless without the ecosystem to support it.
That's a perfect analogy. His polyphase alternating current system was revolutionary because it addressed the entire chain: generation, efficient high-voltage transmission over vast distances, and practical mechanical work at the endpoint.
So, having successfully conquered rotating mechanical machinery and proven that power could be transmitted across vast distances via wires, his ambitions shift entirely.
It goes bigger.
Much bigger. He looks upward in frequency and outward in scale, moving away from heavy mechanical rotors and stepping into the era of high-frequency electrical oscillation and, of course, the famous Tesla coil.
This pivot really represents a fundamental shift in his engineering philosophy. He moves from systems governed by physical rotation into systems governed by tuned electrical circuits, capacitance, and rapid alternation.
So dealing with incredibly fast changes in current.
Exactly. He was exploring what happens when you store electrical charge in capacitors and release it thousands of times per second. And the governing principle of this new frontier was resonance.
Right, resonance. He was chasing it, building these tuned electrical circuits to see what happens when you perfectly match a system's natural frequency.
Resonance is a mechanism of massive amplification. Every physical and electrical system has a natural frequency at which it prefers to vibrate or oscillate. If you input energy into the system at exactly that natural frequency, the energy compounds.
Like pushing a swing at just the right time.
Yes. Or think of acoustic feedback. A microphone picks up a sound from a speaker, amplifies it, feeds it instantly back into the speaker, and within seconds it builds into an ear-shattering screech.
Oh, right.
The energy multiplies because the input perfectly matches the output cycle.
But as you amplify that energy, the destructive potential scales with it.
Right.
Just like soldiers marching in lockstep can cause a bridge to collapse by matching its resonant frequency. Driving an electrical system to its absolute limit has to be incredibly volatile.
It is highly volatile. By tuning his coils to resonant frequencies, he achieved immense voltage amplification, stepping standard currents up to hundreds of thousands of volts.
Which is mind-blowing for that time.
But resonance introduces severe engineering risks. Even microscopic errors in a highly resonant system can lead to runaway energy states. You get extreme heating, catastrophic insulation failure, and totally unstable behavior.
The equipment basically destroys itself.
Exactly. The materials themselves begin to tear apart under the electrical stress. Control becomes just as critical as the magnitude of the power.
Though the magnitude was certainly the focus of his public demonstrations. I mean, he was throwing these theatrical exhibitions, shooting massive sparks across stages, and illuminating glass tubes without any wires attached.
It was a pure spectacle.
Yeah, he was taking these invisible electromagnetic forces and making them brilliantly visible to the naked eye. It looked like magic, which, is a very effective way to convince wealthy investors to fund your laboratory.
Making the invisible visible is a powerful fundraising tool. But the sources highlight a critical boundary that we have to maintain as observers. We must clearly distinguish between a technological spectacle and scientific evidence.
Because they aren't the same thing.
Not at all. A demonstration is not a completed product. Lighting an unattached bulb in a controlled lecture hall proves a localized electromagnetic effect. It does not prove that every massive, futuristic application of that effect is economically or practically viable.
Which brings us directly to the magnifying transmitter and his experiments in Colorado Springs. He left New York because he needed to test wireless power transmission on a planetary scale.
And he needed space to do that.
Yeah, wide open spaces and massive amounts of energy. He built this massive wooden barn on the prairie with a towering mast, generating millions of volts and creating artificial lightning.
Colorado Springs was his attempt to treat the entire Earth and its atmosphere as a resonant electrical circuit. He theorized that if he pumped enough high-frequency energy into the ground at just the right resonance, he could transmit usable electrical power anywhere on the globe without wires.
But here's my question. If a small resonant coil works perfectly in a New York laboratory to light a bulb across a room, why couldn't he just build a massive one in Colorado to light a bulb across a continent? Doesn't the physics just scale up proportionally?
That assumption is the great trap of the laboratory effect. In engineering, scaling is almost never a simple, linear enlargement.
Why not?
Well, when you try to scale a high-frequency system from a room to a planetary radius, you encounter crippling nonlinear losses.
Yeah.
The air itself ceases to be a perfect insulator at those massive voltages and starts bleeding energy away.
Wow. Okay.
You also encounter unpredictable environmental interference from the Earth's shifting magnetic fields and atmospheric conditions. And the materials required to handle that much raw voltage simply break down.
So the environment pushes back. The Earth isn't a perfect, frictionless conductor just waiting to be rung like a bell.
Precisely. And beyond the physics, you hit insurmountable economic costs. Building a global network of massive magnifying transmitters to pump raw power into the sky requires capital that no investor will provide without a guaranteed return on investment.
Which he couldn't promise.
Right. An engineering proposal remains a proposal until it survives those environmental and economic hurdles. A localized laboratory effect does not automatically translate into a practical global network.
So, realizing that pumping massive amounts of raw power into the atmosphere was incredibly difficult, he also pursued a parallel track, which was sending complex information and control signals without wires.
Right, communication.
Yeah, this is the realm of teleautomatics, famously demonstrated with his radio-controlled boat at Madison Square Garden.
That was a huge moment.
It really was. He had a small boat floating in a tank of water, and he controlled his propeller and rudder using invisible radio waves from a remote console.
And this work was part of a broader, highly competitive era where inventors worldwide were rapidly exploring electromagnetic signaling, antennas, and remote operation.
But his demonstration was so tangible.
It was a brilliant demonstration that a physical machine could respond reliably to transmitted commands over a distance.
The public reaction was just sheer disbelief. People thought he was using magic or that there was a trained monkey hidden inside the hull steering it.
Which is hilarious.
Yeah. But because of this, it's very common today to hear people claim that he essentially invented the modern autonomous drone or the first robot with this boat.
We really need to dismantle that false equivalence carefully because it fundamentally misrepresents how modern technology works. His boat was a masterpiece of remote control, but it possessed zero autonomy.
Okay, what is the mechanical difference between what his boat was doing and what, like, a basic drone does today?
The engineering significance of his boat was that it successfully linked three things: sensing an invisible signal through a coherer command discrimination, meaning he used basic frequency tuning so the boat only listened to his specific transmitter and ignored background noise and mechanical actuation, like turning the rudder.
Okay, so it could hear the signal, filter it, and move.
Right. But the intelligence of the system remained entirely with the human operator. Modern autonomy requires onboard computation. It requires machine perception, environmental sensors, and decision-making feedback loops.
So the machine has to adjust its own behavior to avoid an obstacle without human input.
Exactly. His boat was essentially a mechanical puppet on a long, invisible electromagnetic string.
He laid the foundation for unmanned systems. But he wasn't handing the steering wheel over to a computer. He was still doing the driving.
Yes, and understanding that helps us ground him in reality rather than mythology. It also helps dismantle the pervasive myth of the solitary genius.
Oh, that's a big one.
The idea that he operated completely alone, changing the world through sheer isolated willpower, it completely ignores the reality of commercialization.
He had to deal with the friction of the real world. I mean, you can build a perfect system in your mind, but bringing it into reality requires signing contracts, securing patents, finding skilled machinists, and arguing with bankers.
Ideas only survive within economic and social frameworks. True public utility requires massive institutional work. The history of wireless technology is heavily layered with contributions, competing patents, and shared discoveries from dozens of researchers.
It wasn't just him in a vacuum.
Exactly. Recognizing that he relied on investors, legal frameworks, and partnerships doesn't diminish his brilliance. It protects the true nature of creativity by highlighting how grueling the real work of commercial deployment actually is.
It is fascinating how his own autobiography contributes to that heroic, solitary image, though. Because it is his own testimony, written from his subjective viewpoint, it naturally elevates the dramatic, lightning strike moments of inspiration.
And heavily downplays the slow, grinding, collaborative institutional work that actually got the wires strung.
Right. Which is why, as we evaluate his legacy, responsible admiration is our best tool. We are constantly sifting through an incredibly complex mix. On one hand, you have his documented world-changing achievements like the AC induction motor.
Which is undeniable.
Yes. And on the other, you have a mountain of unsupported conspiracy claims and exaggerations about secret weapons or infinite free energy devices he supposedly perfected in secret.
We have to label his output accurately. We can marvel at his future-oriented language because he absolutely foresaw extensive global communication and remote control networks.
He was definitely ahead of his time there.
He was. But we must strictly separate demonstrated historical facts from plausible extensions and separate his engineering proposals from pure speculation.
Preserving those rigorous boundaries actually makes his verified physical achievements far more impressive, I think. It shows what he actually managed to push through the bottleneck of reality.
I agree completely.
The sources outline a deeply practical theory of creative work hidden beneath the spectacle. It's a method. It's not just waiting for inspiration to strike.
Right, it's work.
It's about noticing a friction or contradiction in the physical world, constructing a vivid, disciplined mental model, and then most importantly, testing the consequences safely. Identifying how the materials fail, recording the negative results, iterating and inviting the scrutiny of physical laws.
Sudden insight is wonderful, but inspiration only becomes a reliable tool through rigorous method. A perfect mental simulation is only the very first step.
Yeah.
A perfect thought does not power a city. It takes grueling, disciplined contact with the physical world to turn an image into infrastructure.
Yeah.
And technological capability alone doesn't decide whether a system is actually safe, economical, or beneficial for humanity.
Which leaves us with a final thought for you to consider. When you look at the technological landscape today, which is crowded with massive promises, disruptive proposals, and highly visible visionary founders, how should society evaluate these incoming inventions?
That's a great question.
Should we allow ourselves to be swayed by fame, brilliant forecasts, and theatrical demonstrations? Or must we demand reproducible evidence, transparent limitations, practical, scalable value, and a clear responsibility for the consequences before we hand over our trust and our infrastructure?
It is the exact same question that hovered over his laboratory over a century ago, and honestly, it has only grown more urgent.
To explore these mechanisms further and experience the inventor's perspective directly, we encourage you to obtain and read a lawful edition of the original source material, My Inventions, the Autobiography of Nikola Tesla by Nikola Tesla. See where the boundaries of imagination and engineering truly meet. Thank you for joining us on this deep dive.